Hey everybody, and welcome to Astronomy on Tap Charlottesville. This is our 11th edition of Astronomy on Tap Charlottesville. For those of you that are new to here, my name is Matthew Pryal, aka Buzzed Lightyear, and I am going to be your MC for the event. And so what I'm going to do right off the bat is go ahead and just start sharing my screen, get the right slides up so we can go ahead and get started with the event. Give me 1 second with that. All right. Yeah, and so as I said, this is our 11th edition of Astronomy on Tap Charlottesville. We got a bunch of great talks scheduled for today, a lot of really cool, fun segments as well. And so our tonight's speakers are going to be Dr. Michael Küffmeier, aka the Cosmonaut, joining us all the way from Copenhagen. Abby Waggoner is going to be talking to us as well, aka Astrono Abby. And then we're going to be joined, our final talk of the night is going to be Dr. Jeffrey Bennett. And again, I'm the host, Matthew Pryal, but unfortunately, I got to start with some bad news. And that's that I've been informed by the university that I can no longer go by my Buzzed Lightyear costume, or the Buzz Lightyear moniker, despite the costume. And that is because I am now officially Dr. Buzzed Lightyear. And so, yes, since we last spoke, I have defended my PhD and have been awarded my PhD, and am now officially Dr. Buzz Lightyear for the remainder of our Astronomy on Tap event. So, woo, that's great celebration. All right, so let's go ahead and get going. So for those of you new to Astronomy on Tap Charlottesville, I just wanted to give you a quick introduction. We were founded by University of Virginia graduate students in October of 2018. And so the whole idea was, of course, to bring astronomy to the Charlottesville community in a fun and relaxed setting. Ever since the pandemic happened, we've turned towards virtual events rather than having our events hosted at bars, such as these pictures for bars located around Charlottesville. But it's been really fun doing our virtual events, and we're going to continue to do them every 2 months going forward for the foreseeable future. All right. And so for tonight's schedule, the way that the schedule is going to break down is Michael is going to be doing the first talk in just a couple of minutes. It's called A Star is Born. It's going to be about star formation. We have a new segment called Astronomy in the News. Ed Murphy is going to be talking about some fun astronomy things that have been in the news lately and some things coming up in the future. Abby Waggoner is going to be talking about how astronomers observe molecules in space, and her talk is entitled Watching Molecules Dance in Space. Of course, it wouldn't be Astronomy on Tap without some trivia, so we'll have some trivia as well. Follow that up by What's Up with Levi Schultz, where Levi is going to be talking to us about what's up in the night sky. And then finally, Jeff Bennett is going to be talking about global warming demystified, a cosmic perspective. So it should be a really fun night. And so typically with Astronomy on Tap, we like to raise donations for some type of Charlottesville community as our way to support different Charlottesville area organizations. And since February is Black History Month, in celebration of Black History Month, we are going to be raising money tonight for the Albemarle Charlottesville County NAACP branch. And so typically any money that you would have been using to pay for, if we were at a bar, to tip your bartender or anything like that, please donate as much as you possibly can to the Charlottesville NAACP. There should be in the chat, I think Catherine or somebody should be sending some links where you could, let me see, bring that up. Yeah, and so it should be sending some links where you can donate, and please just donate as much as you possibly can. Any little bit helps. All right. And so typically, despite the fact that we're doing this all through a virtual setting, we're trying to make this as interactive as possible. And so we always begin by asking you guys a couple of questions about who's watching. And so the first question, the first poll that I'm going to pose to you guys is, where are you watching from? And so Catherine, if you can go ahead and make that poll live and make sure to just fill out that poll. Let us know where you are watching from. Charlottesville, Albemarle County, elsewhere in Virginia, outside of Virginia, or maybe even outside of the US. I'll give you a couple of seconds to fill that out. Unfortunately, I don't have the ability to vote. Otherwise, I would be voting Charlottesville. I am watching from Charlottesville. Since I graduated from grad school, I've become an instructor at the University of Virginia Astronomy Department. So maybe some of my students are watching tonight. If so, I'm embarrassing myself with my Buzz Lightyear costume. So Catherine, go ahead and make the results known. There we go. Yeah, so it looks like the majority of people are actually watching from Charlottesville and Albemarle County. We do have about 20% from elsewhere in Virginia or outside of Virginia. If you guys use the chat, you can let us know where you're watching from as well, if it's elsewhere from Charlottesville than Albemarle County. But yeah, so let's go ahead and bring up the next question. What are you guys drinking tonight? It's Astronomy on Tap after all. I'm drinking some wine tonight, a very special wine from the south of France, or is it Franzia? Yeah, it's Franzia. That's what I'm drinking. So I'm drinking some wine tonight. We'll see what you guys are drinking. Of course, you don't have to necessarily be drinking alcohol. Astronomy on Tap's for anyone, not just for those that are drinking alcohol at the events. Try to make it as fun as we possibly can for everyone. I'm going to submit that for me. Oh, I'm finally seeing the congrats Dr. Buzz Delight ears over here. So thanks for the appreciations, guys. All right, Catherine, maybe you can go ahead and make those results known. We got lots of people drinking water tonight, a couple of beers. 15% of people are joining me with wine. I love it. And then we got some coffee and teas. Nice. And we got some others. If you think we should put some other things in this going forward, please let me know what we should do in the other category to include some more different types of beverages. But anyway, yeah. So what's question number 3? What's your astronomy experience? And so we're always trying to make this event as available to everyone. You don't necessarily just have to know astronomy, but are you a professional astronomer, an astronomy student, amateur astronomer, just a fan, or even none? It's great. We typically love seeing the people that have no astronomy experience trying to watch some of the events. It's always very fun. And so hopefully you find some enjoyment out of astronomy after this if you don't have any astronomy experience at all. So go ahead. I'm now having to click a different answer than astronomy student, unfortunately. So Catherine, go ahead and reveal the results for us. We got lots of fans. About 43% of the people are fans, a good amount of professional astronomers. And we even got some people that don't have any astronomy experience at all. Very good. All right, and the final question of the night is, when is the last time you guys looked through a telescope? And so despite the fact that we got a lot of professional astronomers watching, I know it's probably been quite a while since people have actively looked through a telescope, but that's often sometimes some of the most fun things you can do, pulling out your telescope, looking at the moon, looking at the Orion Nebula, some other globular clusters in the night sky. And so I've done it within the month. It's been a pretty busy month for me, but I have looked at the moon within the month. The moon's probably one of my favorite objects to look at through a telescope. Let's go ahead and reveal those results. Too long to remember. So over a year for a lot of people, 28% of people over a year at the very least, 26% of people about a year, and 26 more about a month. So if you guys have the opportunity, try to look through telescopes as much as you can, of course. I know with the pandemic, it's been pretty difficult lately. If you get your own telescope, for $100, $200 online, you can be able to do some own observing of your own in the night sky. All right, so that wraps up the question portion. And so now what we're gonna be moving on to is the first talk of the night. What all of you guys came here, rather than me bumbling about trying to get to know you. And that's of course from Dr. Michael Küffmeier from the University of Virginia. And so Michael, he is a postdoc at the University of Virginia. But he's currently working remotely from Copenhagen in Europe. And so he's joining us at about 1 a.m. This is how dedicated Michael is to doing outreach and speaking at Astronomy on Tap. And his work focuses on modeling the formation of phases of stars and on understanding disks of cool gas and dust that surround them. And his talk is entitled "A Star is Born." And so I'm going to stop sharing my screen, turn my video off, and hand it over to Michael.
The tale of the sun's birth. Once upon a time, in a galaxy called the Milky Way, there was a cloud of gas and dust. This cloud became so massive that it collapsed and formed thousands of stars. One of the stars was the sun. Shortly after the sun's birth, 8 planets formed around it: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. After this short period of formation, that means a few million years, the sun, together with its planets, lived a relatively calm life for more than 10 billion years. Earth had a midlife crisis at the age of 4.567 billion years, struggling with humans who couldn't have their beers on tap, but the sun didn't really bother about it. Eventually, the sun evolved to a red giant and ended its life as a white dwarf, but that's another story. Instead, let's hear more about how the sun and other stars came into existence.
Yeah, thank you very much, Julia. Thank you for telling us very nice tale as an introduction, and also thank you, Matt, for having me here. And let me say cheers to all of you in Charlottesville. It's a pleasure for me to present some of my research here in Astronomy on Tap, although it's not real Astronomy on Tap, it's the Quarantine edition. What's happening here? Quarantine edition, here now it works. And so we have to have like Astronomy on Can, or Astronomy on Cup, or whatever you prefer to drink of. All right, so what I will talk about is A Star is Born, and Julia already told us beforehand this tale about the sun, and I will, in the next couple of minutes in my talk, I will explain to you a little bit more what is it about, maybe from a bit more of a scientific point of view. All right, so before we start, let's just make sure that we know what we are talking about. What is a star? Well, a star, according to the Oxford Learning Dictionary, is a large ball of burning gas in space that we see as a point of light in the sky at night. And as we saw, there are a lot of astronomers here, a lot of fans. So I guess it doesn't come as a surprise. So you apparently all looked up in the night sky, and you see plenty of stars there. What is the key point here? What I want to point out is this point of burning gas in space. So burning gas, that means there's fusion of hydrogen going on that defines a star. And in fact, what I will talk about today is just the period before this burning happens. So really the formation of the star before it starts burning the gas, just to keep that in context, that this is what we're looking at. So it's really a brief period, relatively brief period, that we cannot necessarily see just by the naked eye, with the naked eye. So where do stars form? Stars form in so-called molecular clouds, and these molecular clouds are 10 to 100 parsec in scale. That means it's about 2 to 20 million times the distance from the sun to the Earth, or if you like to think in light years, this is about 30 to 300. They're about 30 to 300 light years across. Why are they called molecular clouds? Well, they are called molecular clouds because they mainly consist of molecules. So stars are forming made from molecules there in these clouds. To illustrate the sequence this one really nice cartoon here. Credit goes to Bill Sexton at NRAO in Charlottesville. And I will briefly guide you through this, how a star forms. So you have like the cloud of gas here, this molecular cloud. During the time of evolution, you get a smaller, you have some chaotic motions, you start forming more and more structures inside the cloud. And eventually, some of the gas becomes so dense that gravity takes over. So there are these filamentary structures, and what you get is you get clumps of gas that are collapsing due to their own gravity. And then you can imagine you're left with like somewhat like a ball that then starts to collapse, and while it's collapsing, if you just imagine something without any other force, without anything else, it's collapsing, and you end up with a star at the center. However, there's also some rotation, some intrinsic rotation going on here. So what happens then is most of the mass is falling towards the center, but then there's also the vertical component cancels out, and the net horizontal component is conserved. So what you get a star in the center, while at the same time you start forming this disk around the star. And this disk matters because the disk is really the birthplace of planets. And without this disk, we wouldn't have the planets. And this is obviously of existential importance for us on Earth. So this is really the sequence. You go from the cloud to these smaller structures that eventually become gravitational unstable, and then you end up with the system of a star and a planetary system on the smaller scales. So to point that out, here is that stars and planets are really the smallest entity in a hierarchy of scales. And to show you a nice video here of a collaborator of mine, I think illustrates this quite nicely. So this is a computer simulation of such a molecular cloud, where you then see these dots, and they represent the stars, and you see the color scheme that corresponds to these to the filamentary structures within this molecular cloud. And what you can really see here is that stars are embedded in different locations here in the molecular cloud, and they are forming in different birth environments. So to put it all together here again, so keep in mind, stars, they are really forming these molecular clouds, which is the birthplace, and that these stars form in different locations in these structures. Well, this is known for decades already, but what modelers typically do, they don't really care about these clouds so much. So it's like, okay, fine, we know that that stars form within these giant molecular clouds, but this is all very complicated and it's really hard to model. So what is often done is a so-called spherical co-approach. And what it means, well, it means this. It means instead of, so imagine you have a cow, you can see there's a lot of structure, you have like a lot of features here, and this is very complicated. So instead you just say, fine, we just approximate it to be a sphere. And this is nice because it simplifies the problem a lot. So instead of having all these features that you have to take care of, you just say it's a completely symmetric problem. And this can really help to get a lot of understanding of the physics of the physical processes, because the problem design is quite easy. However, in reality is of course a bit more complicated. And the good thing is now we don't need to do these things anymore, and that's in fact what comes to the research I'm doing when modeling a star. So I've been following a different approach, and this approach is it's really like, let's face it, stars are formed are the smallest structures, are the smallest entities of these in this large hierarchy of scales, and we have the computing power. So what I've been doing already for some time, and what I'm really working on also here as a postdoc at UVA, is to run computer models. And you can see here a nice image of these simulations of such a cloud, and you see all these sprinkles, this structure here, and these bluish regions here. That's where stars are forming. So what we then can do is we basically take a zoom. So we apply high resolution just in the region where we're interested in, and then we can resolve the processes here with high resolution while still accounting for everything around it. So we don't need to assume like an idealized initial setup. We just have everything. We keep everything here and go down the scales, and then you can go here on these core scales, as we call it, and you can see here at the center there's a star forming, and in fact we can go all the way down then to a U scale, so to the scales of a disk, what you can see here, and then we can run this video. We can simulate the process of a disk, and note here the sizes here. This is 20 AU, while the entire box that you saw beforehand, that's about 10 million times bigger. So it's really just to emphasize this huge range of scales. And here you can see in this video the zoom in on such a disk around a star, of a young forming star. And you can see how material is falling in. There's a lot of structure going on in the disk. And it really illustrates that there is quite something going on. And in general, what will be interesting also now is to follow up more on these, how this disk is fed potentially from the surrounding. And that's, there's really a lot of stuff going on for the next, in the near future, which is, I think, really excited to look at. And that's really something I'm looking forward to carry out. Okay, to show you then another movie here which is maybe slightly less exciting. It's just a projection plot, but it shows you like really the zoom in. So you really start from the large scales. Sorry for the color scheme, it's not that clear maybe, but you can, yes, we are really going from large scales now down to the disk. And you can see here, you see these structures there. And while we are going through all the scales, you can see that there's really the resolution is really just applied where needed, while you can see the other regions are less resolved. So this is the method that we are using to allow this. And then we are going down all the way to the disk scale. Well, this is fine so far, but the ultimate goal is, of course, then to compare these disks with observations. And there's been a lot of beautiful work being done in the last couple of years, especially with the ALMA telescope. And the ultimate goal is really to run these models and then really to compare how what's similar, what's different, what are really the physical processes going on that can explain these beautiful observations. And I think with this, it's the end of my talk and my presentation here. And just to put everything in context again, let me remind you on how the star is forming. So how is a star born? Well, you start with the cloud. Here, this is the initial state, the molecular cloud, which is then, due to some density fluctuations, becomes gravitational unstable. So you start from having dense structures there, which then collapse due to their own gravity. You end up with the star at the center that's forming, and due to the rotation in this collapsing ball of gas, you end up with a disk. And I just want to point you here to this QR code. I think there's a very nice analogy given how a disk forms, similar to making a pizza in space, because I think there's quite often maybe like a misconception that the formation of a disk is explained similar to a pizza dough. So you have like a pizza, when you have the pizza dough, you spin it and then the disk is forming. But in fact, what's really happening for the disk that's forming over the star is in fact that it is like much smaller than this initial ball. So I think this little article here that you can see in this QR code explains this quite nicely. So if you're interested in it, feel free to scan it. So then should we go further from this disk, we go to the stellar system. So the planets form in these disks, and this is really where we are now. This is going on for billions of years, and eventually such a star will end its life and lose its mass again. And the nice thing is then it will recycle again in such a cloud, and the procedure can happen again. And so I want to say thanks for your attention, and thanks for having me here. It was a pleasure.
Awesome. Thank you, Michael. That was great. And so at this point, I always forget to do this at the beginning of the talk, but I do want to remind people that we're still accepting questions. You can do that two ways, either through the chat, which a couple people have already, and there's also a Q&A feature. And so you're still welcome to ask questions to Michael at this point. But Michael, I do have two questions right immediately. The first one is from Dennis Plews, asking, what's the minimum mass of a POP3 star? So maybe you should go ahead and explain that to some people as well.
Okay.
That might not know what a POP3 star is.
Yeah, so POP3 star, that's like considered as the earliest star. So in the context of the universe. So what I've been talking about mostly here is the formation of low mass stars. And POP3 stars, they are really considered as the earliest stars. So they are forming a couple of 100,000 years after the origin of the universe. And in order for them to collapse, you at the beginning of the universe, you basically only have gas, and you don't have any heavy elements, and so you need like a lot of mass to collapse them. So they're supposed to be like the first stars, but they're also enriching the universe. So that should be then should be a mass of at least 8 solar masses, probably even more, if I'm not mistaken. Yeah.
Okay, cool. All right, so we got another set of questions here from Eric Anderson. Eric asks, why are stars formed in such a wide range of sizes? Do we have a good idea of the distribution of large and small stars? And what about objects almost big enough to start to glow, but that wind up too small to start fusion? So you can tackle any of those, I think, that you want.
Yeah, so we have a good idea of the distribution of stellar masses. It's so-called an initial mass function, and yeah, it's a bit hard to how do I don't think I can really draw it here, but it's such a function basically. So most stars are low mass stars, but then you have like only very few high mass stars. So high mass stars, the range of star masses is really then about 0. So the limit really is that that you have as you said, it's related to the burning of hydrogen, and so you can also have like so-called brown dwarfs, where you have like burning of deuterium. So that's it's happening as well, and the minimal mass there is about 80 Jupiter masses that you need for brown dwarf, and then you can span all the way up to to 100, even 100 of solar masses. But these very high mass stars, they are very, very few of them that we have. So I hope that that's roughly fine.
All right, awesome. Well, thank you. It doesn't look like we have any immediate questions right now, unless let me just check my messages. Oh, there's one final question. I think we have enough time for the last one. Have any POP2 stars with planets been detected? Is the question.
I must say I don't know the answer. So does anyone know? So if anyone knows, please share it.
Yeah, any of the professional astronomers out there in the chat are welcome to let us know, and we can chat back some of the answers as well. But yeah, I think for now that's all the time we have for you. So thank you so much, Michael. That was an awesome talk. Thanks for joining us so late and and for cracking a beer at 1
I can
a.m.
feel it. I can feel it.
We really much appreciate it. And yeah, I think Michael might be signing off because he might be going to sleep. But if you have any questions, feel free to include them in the chat, and we might be able to get them to Michael at some point. But thanks, Michael.
Thanks.
All right, so for now, what we're going to do is I am going to, next up is actually not you, Ed. Thank you, but unfortunately, Ed revealed his video. We're actually going to go to Scott Dureski from the Charlottesville Astronomical Society. And Scott's going to talk to us just very briefly about CAS. For those of you guys that are interested in astronomy, there's this great society called the Charlottesville Astronomical Society in Charlottesville. And Scott himself has been a dedicated member of the Astronomy on Tap Charlottesville community and the Charlottesville Astronomical Society. And so he wanted to take just a couple of minutes just to highlight that for you guys. And I'm just going to share my screen so that you guys can see some of the information about CAS while Scott talks. And so you can go ahead and unmute yourself, Scott.
I am unmuting. Good evening, everybody. I'm Scott Dureski. I'm the Vice President and Observing Director of CAS. And for those who might ask, what are we doing right now? Well, obviously, we're not doing much more beyond monthly virtual meetings such as this one. However, I can tell you that in the future, when the coast is clear, we have an excellent dark sky observing site that we go to regularly, and we have a number of star parties planned in the future, and quite a few things going on. For those of you who follow the website of the CAS or the Department of Astronomy, the coast of clear, so to speak, is when the University of Virginia's Department of Astronomy officially clears the McCormick Observatory for reopening. At that point, it'll be open to regular club meetings, and the Charlottesville Astronomical Society will resume their full program of club outreach. And hopefully that announcement will come sometime in September or October. We hope earlier. Obviously, that's a long time from now, but at this point, we all have to have hope for the future. And all I can say is there are a lot of things going on that are very exciting. And we'd like to, if there's anyone out there who would like to know more about what we're going to be doing later on, anybody out there who may be interested in finding out about some of the loaner scopes that we lend out to people who'd like to learn more about astronomy. We do have a very active mentoring program. We've got a lot of things actually that we are doing right now for people who are interested in learning. For any of you out there who is listening to this, what I encourage you to do is to stay on and listen to the entire program this evening. And when it is finished, Matt will turn it over to me again. And at that point, any of you who would like to give me information about how I can get in touch with you later, you may certainly do so. And I encourage you to do so because There are exciting things going to happen in the future. We just can't do them right now. And thank you very much for your time, everybody.
All right, thanks so much. Thanks so much, Scott. That was great. Yeah, we should be posting some links in the chat for anyone that wants to see more about the Charlottesville Astronomical Society. And you can also ask some questions via the chat or the Q&A that we can pass on to Scott, maybe towards the end if we have some time for that. But for now, what we're going to be doing is we're going to introduce a new segment to Astronomy on Tap Charlottesville. And this one does involve Ed Murphy from the University of Virginia. And so Ed, for those of you guys that don't know, he's a professor of astronomy at UVA. He's actively involved in a wide variety of astronomy outreach, including Astronomy on Tap. And he's going to be talking to us about astronomy in the news. And so you can go ahead and take it away, Ed. And of course, if you guys have any questions, feel free to ask them in the chat as well, and Ed can respond to that either in the video or just via the chat. And go for it, Ed.
Thanks, Matt. Thanks very much. So I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy in the News. So let's go ahead and get started with the breaking news that we have. Within less than 12 hours from now, so less than 12 hours from now, the United Arab Emirates Al Amal, which is Arabic for hope, spacecraft, will enter orbit around Mars. This is the first of 3 spacecraft that'll be entering orbit around Mars in the next 2 weeks. Al Amal is designed to study the atmosphere and the weather on Mars, and it will spend the next year or so compiling daily and seasonal weather, Martian year, I should say, which is about 2 Earth years, daily and seasonal weather on the surface of Mars. Al Amal was launched this past summer by a Japanese rocket, and it should enter orbit tomorrow at 10:41 a.m. if all goes well. On top of that, less than 24 hours later, the first Chinese spacecraft going to Mars, called Tianwen-1, will enter orbit around Mars. Tianwen-1, which stands for Heavenly Questions, consists of 3 parts. There's an orbiter that will remain in orbit around the planet Mars, a lander that will go down to the surface, and that lander also contains a rover that will rove across the surface of Mars. For both the United Arab Emirates and China, these are their first interplanetary probes. And then 10 days from now, on February 18th, the Perseverance rover will land on Mars. This is NASA's next giant rover to land on the surface. Of course, we have this armada of spacecraft going to Mars. People have long been fascinated by the idea that Martians might gather their strength and come attack the Earth. This is a diagram from H.G. Wells's famous War of the Worlds. This was the 1898 edition of the book. And in fact, the tables have been turned on Mars because we have there today an armada of spacecraft in orbit around Mars. This is a fantastic diagram that shows you all the robots that we have operating across the solar system. I don't have time to go through all of them, but if you look in this upper left corner, you can see what we have in and on Mars today. Down on the surface, we have the Curiosity rover is still operating. We have InSight, which is looking into the interior of Mars. We'll hear more about that here in a second. In orbit around Mars, we have the Mars Odyssey, Mars Express, the Mars Reconnaissance Orbiter, the MAVEN spacecraft, the Indian MOM spacecraft, and ExoMars TGO. And they'll be joined here in the next 2 weeks by these 3 spacecraft, Perseverance, Tianwen-1, and Al Amal. For those that aren't familiar with the mission of the Perseverance rover, it is built on the same chassis and design as the Curiosity rover that's currently on Mars right now. Its mission will begin on February 18th when it enters the Martian atmosphere at very high speed. A heat shield will initially slow it down. That heat shield will be ejected. A parachute will come out to slow it further down, but that parachute can't slow it down enough to land. So the rover has to drop out of this back shell and come down on rockets. And it uses a maneuver called the sky crane maneuver. From beginning to landing, the total length of time is about 7 minutes. What's fascinating about these landings is that the transit time for radio waves from Earth to Mars at this time is about 14 minutes, which means the rover has to do this all on its own. By the time the rover lands on the surface of Mars, after that 7-minute flight, Here on Earth, we are 14 minutes behind, so we won't know whether it was a success or not for another 14 minutes. The goal of the Perseverance rover is to search for past and even possibly present life on Mars. As I said, it's built on the same chassis and design as the Curiosity rover, but it has a whole different set of scientific experiments that it's carrying on board. If you're going to look for life on Mars or past life on Mars, the place to go look is someplace that used to have water. And they have selected the Jezero crater. The Jezero crater has a diameter of about 30 miles across, and it's a great crater for this because it has what looks to be an inlet channel and an outflow channel. It appears that at some point in the past, Jezero was filled with water, probably 3.5 to 4 billion years ago. And that water, of course, has since evaporated. But looking at the crater today, we can see what appears to be a delta deposit. As this river flowed over a long period of time, it deposited sediments in the lake that filled this crater. And as those sediments built up, you can actually see multiple channels here where the river used to flow on the surface of Mars. As these sediments built up, they may have trapped evidence for past life on Mars. Or, since there was lots of water here in the past, this is an excellent place to look, as Perseverance will do, to look for the possible presence of current life on Mars. The goal is to land just off the end of the delta here and then spend the next few years driving up onto the delta, exploring the delta itself, and then driving up and exploring what used to be the shore of the lake, and then following the rim of the crater. Perseverance, in addition to the Perseverance rover itself, it's carrying a helicopter on board called the Mars Ingenuity helicopter. A few weeks after it lands, it will drop the Ingenuity helicopter on the surface, and then the Ingenuity helicopter will actually conduct up to 5 flights on the surface of Mars. Now, the thing to know about Ingenuity is it is a technology demonstrator. The goal of Ingenuity is not to accomplish any science, but just to demonstrate that flight on an alien world is possible. So it'll conduct these 5 flights, and then it'll be set down, and Perseverance will go on with its mission. But the hope is that this will lead to future missions in which small helicopters like this can actually fly across the surface. And probably the most interesting thing that Perseverance will be doing is, as it moves across the surface of Mars and finds interesting samples, it will be caching those samples. It has a series of sample tubes. It will be putting the samples in those tubes. It will be driving them back to a central location where those samples can be stored so that a future mission can come pick them up and retrieve those Martian samples. Now, there was some recent bad news from the surface of Mars, and that concerns the InSight lander on the surface of Mars. The InSight lander had 2 main scientific instruments, a seismometer that was to measure quakes on Mars and a heat flow probe that was to go down into the surface and measure the heat coming out of Mars. Unfortunately, the heat flow probe was never able to bury itself, and NASA recently abandoned that. Other news in astronomy concerns the discovery of what's called a redback pulsar. Redback pulsars are pulsars that are in the process of devouring their companion stars. In this particular case, it was discovered with the Fermi Space Telescope. It was pulsing in gamma rays, and they used the Einstein at Home Citizen Science Project. The computing power required to see these pulsations was far too much for an individual computer. So they used people's home computers to discover the pulsing nature of this pulsar. And they're called redbacks because there is a spider in Australia called the redback spider that's famous. The large female consumes the small male after they're done mating. And in this case, this pulsar, which is the more massive of the 2 objects, is consuming or eroding away its companion star. And other recent news is that a small dwarf companion galaxy to the Milky Way called the Tucana 2 ultra-faint dwarf galaxy. Astronomers found some stars in the distant halo of this galaxy. Those stars were interesting for a couple of reasons, one of which is they are so far out, but still bound by gravity to this small dwarf galaxy, that the galaxy must contain a very significant amount of dark matter. In addition, these stars have less than 1/1000th the amount of heavy elements that our sun has, making those stars in this galaxy some of the most metal-poor galaxies and the most metal-poor galaxy and some of the most metal-poor stars known. That means that this dwarf galaxy, Tucana 2, is likely a very good example of the first galaxies in the universe. Coming up here in just a couple days, on February 20th, there will be a launch here from the Mid-Atlantic Regional Spaceport. Northrop Grumman will be sending a new spacecraft up to the International Space Station called the Cygnus NG-15. That is Saturday, February 20th. Should be visible from all over Central Virginia if they get the chance to go outside and watch it. So that is the news that I have for today. Thank you very much. And back to you, Matt.
Thank you very much, Ed. That was amazing. I didn't realize there was going to be so many noises and stuff to go along with it at the beginning. We're definitely going to have to incorporate that into all Astronomy on Taps moving forward. And it was great to see your guest as well make an appearance for a slight bit. I think, if we stick answering to questions to a minute, would you mind answering a couple of questions that we have in the chat?
Yep.
And so one of the first questions, we'll do 3 questions. It was, what types of environments and conditions will Tianwen-1 explore on Mars? Sorry, I'm not saying it correctly, but.
No, Tianwen-1. So the goal of this, I think, first of all, it's a Chinese mission, and not much is known about the specific goals or the scientific instruments that are on board in the West. So we don't know everything that it's going to do. I would argue, since it is their first mission to Mars, it is very likely to be a technology demonstrator. That is, they want to demonstrate this ability to go into orbit around Mars, land on the surface, and rove across the surface. You're probably familiar with the fact that China has recently landed 2 rovers on the moon. And as time goes on, they will get more and more sophisticated.
Sorry. Yeah, great. That's awesome. Another question is, to what accuracy in terms of location on Mars can the rovers land?
So it's a great question. With Perseverance, they've been able to get that landing ellipse down to just a couple kilometers in size. Back in the days of the Viking missions in 1976, the landing ellipse was many, many tens of kilometers in size. But today, thanks to being able to actively guide the spacecraft as it's coming through the atmosphere and actually use the fact that that it flies a little bit and use some of that lift, they can guide it down, and the hope is that they can get it to within a few kilometers of the expected landing site.
Oh wow, that's really cool. Actually,
Yeah.
I didn't think that much. Okay, final question. We only have time for one more. The question was, is there anyone monitoring all the Mars crafts so they don't crash? So maybe you can talk a little bit about this, just the monitoring of them.
Yes. So when it comes down to being on the surface of Mars has about as much surface area as the land that we have here on the surface of the Earth. And there are only a few rovers on the surface, and they are spread across the planet. So we never have to worry about that. My students often ask if the rovers will ever meet one another. And the answer is no, because they are thousands of kilometers apart. And in the typical life of a rover, it only drives about 50 kilometers or so, in the case of Curiosity, for example. When it comes to orbiting the planet, even though it looks like we have a lot in orbit, space is huge. There's lots of orbital space, so we don't have to worry about monitoring the space around Mars that the satellites might collide with one another. We have, after all, around the Earth, tens of thousands of satellites, and they hardly ever collide with one another.
All right, well, unfortunately, that's all the time we have for Ed. Thanks so much for some good news over the past 10, 15 minutes. We look forward to more astronomy in the news segments in the future. I think it's going to be a hit going forward.
Thanks, Matt.
But for now, we're going to turn to our second talk of the night. And our second talk is by Abby Waggoner, aka Astrono Abby. And so Abby is a graduate student at the University of Virginia. And with her research, Abby studies the chemistry of planet-forming regions, but she's also really actively involved in outreach, including Dark Skies, Bright Kids, which is an outreach group at the University of Virginia Astronomy Department. And she's also a writer for what's called Astrobites. But Abby's talk is entitled, How Do Astronomers See the Universe? And she's gonna go ahead and take it away. So go for it, Abby.
Yeah, hi, thanks, Matt. So yeah, I did kind of last minute change the title because I ended up adding a little bit more information than just dancing molecules, but you'll see in a second. All right, so yeah, so the main topic of this is, how do astronomers see the universe? And the answer is by dancing. So to first explain how I'm comparing viewing the universe as dancing, I want to talk a little bit about actually seeing the universe. So we've all seen these really awesome, beautiful pictures that astronomers when NASA release of nebula and galaxies and stars and all these crazy images. So here I have a picture of the Crab Nebula, which is basically it's a star supernova and exploded, and now there's all this mass and particles blowing away from it. And these nebula are just absolutely beautiful when we see these pictures. And based on like what we were saying earlier today, if you've had the wonderful opportunity to like use an actual ground telescope in your backyard, or maybe an Astronomy on Tap event, and if you've been lucky enough to see one of these nebula, or I should say maybe not super lucky because you probably saw something that looked like a foggy white blob, maybe. So the question kind of now comes into, okay, how do astronomers see these awesome, great visuals? And yet when we look with our eyes or with a telescope in our backyard, we're more likely just gonna see a blob. So to answer that, we have to first figure out, okay, what actually is light? So light is two things. First off, it is a particle, like an electron or an atom, kind of, or a baseball, if you'd like to consider it like that. And the name of a particle of light is a photon. So matter, or it has mass, but light is also something called a wave, meaning it's not matter, we cannot touch it. But it is energy in itself. And so if you've ever heard of this is something called the wave-particle duality of light, meaning it is both of these things, even though conceptually it may not make sense. To me, it certainly doesn't. As a PhD candidate studying astrochemistry, I really struggle with this concept, to be honest. So it's okay if you do too. It's just something that math tells us is true and we have to accept it. So now that I've kind of explained what light is, it's these two things, I want to take these two different aspects of what light is to try and help explain how astronomers view space. And so first off, I want to start off by focusing on the photon, or the particle part of light. And so we can use the photon to better understand what brightness is. So if we're looking at something that is emitting light, or just anything like around our house or anything at all, we actually see things because our eyes collect photons, they collect light. And based on the number of photons that our eyes collect, that determines how bright or how dark or how dim something is. So if we only see a few photons, that would be a dim object. But if we see a whole bunch of photons, that would be a very bright object. And so the same concept applies to when we're looking at stars or other objects in space. So if this star is emitting lots and lots of light, lots and lots of photons, if each one of these yellow dotted lines is an individual photon, our eyes are only able to pick up a certain number of these photons. And unfortunately, our eyes are even more restricted because we can only collect photons in a single frame of time. We can't stare and just continuously add up all of the light that we see over a long period of time. We can see one snapshot. Now, fortunately, astronomers are not quite as limited to just our eyes because we have telescopes. So when we use a telescope, first off, they're a lot bigger than our eyes. So when these stars radiate light, they're able to collect a lot more individual photons in a single time frame. And not only that, but telescopes are not limited to just 1 minute in time. We can stare and collect all the photons over long periods of time. And so when our eyes view something in the sky, we may see something kind of like this, number of photons, meaning it would be about that bright. If remember, more photons mean it's brighter, so we could see more structure and more individual parts of an object. But an astronomer might view something like this in the same time frame using a telescope. And then we can keep staring at it with the telescope and see lots and lots and lots and lots of photons. And so this is one of the main reasons why when astronomers are able to take these pictures of objects in space, we get these really great, grand, detailed structures when our eyes looking through a telescope on our backyard might just see a white blob. So this is one of the main ways that astronomers are able to get such detailed pictures. But not only that, astronomers are able to use all types of light. So now we're going to start moving away from the photon definition of what light is, and we're going to use the definition that light is now a wave. And so the way that I'm going to kind of use the word wave here is each individual type of wave means a different type of color. And so what do I mean by that? So if I have a pink piggy bank that I'm staring at with my eye, then say that piggy bank is going to emit light, emit a certain color of light. It will be a wave of a specific wavelength, meaning in this case, our waves are kind of big. So that means it's lower energy. And so our eyes are able to see and perceive these different wavelengths, these different energies of light, and say, okay, that's pink. Or alternatively, if we have like a yellow rubber duck, our eyes will be able to say, oh, you are emitting a different kind of light, a different color of light, and a different wavelength. And so I know, my eyes know, this is yellow. And so our eyes are really awesome, cool tools that are able to detect these different wavelengths that are able to perceive many different colors. But unfortunately, our eyes are actually limited if we want to consider all of the different types of light. So the colors that we can see, or the rainbow, is defined as the visible light. But in reality, there are many different kinds of light, ranging from gamma rays and X-rays, which are incredibly energetic, and also really low energy waves with really long wavelengths, so radio light or microwave light. So our eyes that are restricted to this itty bitty section of visible light cannot tell us everything that's going on. They cannot give us a complete picture of everything happening in the universe. But astronomers, again, we're not limited to the visible light spectrum because we have lots and lots of telescopes that are allow us to look at all the different types of light that tell us all the different things about the universe. And so we're able to learn different things about the universe from different types of light because of the way light interacts with matter. So, or with materials or molecules or anything like that, or all of it, I suppose. And so this science topic of how light interacts with matter is something called spectroscopy. It's a big fun word, it's hard to say, but that's okay. That's all we need to know, is that it's how light is interacting with matter. And instead of using the word spectroscopy now, we are going to switch it up and we're going to use the word dancing. Because effectively, understanding how light interacts with matter and molecules is basically just a big fun dance studio to see how the different molecules are dancing. All right, so for this talk, I am going to be focusing specifically on infrared, microwave, and radio light. The other types of lights are a bit more energetic, and they start to change it up a little bit, whereas this group is a little bit more related. So we're going to start off with radio light. So what exactly do I mean by how light interacts with matter, first of all? That's a weird thing to say. So if we have a ballerina on a dance floor, now if a ballerina spins, we can pretend that when that ballerina spins, she emits light. So if this ballerina spins really slow or kind of slow, she may emit a red light at a long wavelength or a low energy. But if she spins really, really fast, she may emit a high energy color, or a high energy wave, may emit light at high energy or low wavelengths, excuse me. And so we can kind of think of this as when a ballerina spins and dances, that unique dance move has a unique type of energy associated with it. And so now that we have this kind of understanding that every unique move and way that this dancer spins is a unique type of energy, we can apply the same type of logic to molecules. So if we look at a water molecule, which we have here on the screen next to our ballerina now, water and other molecules can spin just like our ballerina. And so when these molecules spin, they are emitting light. And so when they emit light at a very unique energy that only that exact spin of that exact molecule will emit. And so when astronomers, we take our big telescopes and we point them at the sky, we can, and we collect light. When we detect light at that exact energy coming from something, we know, because nothing else emits light exactly like that, that we know that water is in the sky at that, or is in the universe at that location. And also just a fun fact with spinning water molecules. Microwaves that we keep like in our kitchens operate by utilizing this rotation that water can do. So our microwaves actually work because they emit microwave light. And that energy is absorbed into water, which spins really fast. And then all that spinning gets converted into thermal energy or heat. And so microwaves heat up your food by shining light on them and making water dance. So very fun. All right, so astronomers can use radio and microwave spectroscopy or astronomy, which is all about the dancing and spinning molecules. So look at different objects in space. One of the big ones in my mind, because I'm an astrochemist, is we can actually identify individual molecules in space, which is absolutely wild to me. I still do it every day and I still can't get over how cool it is. And so this is really neat because it tells us about chemistry within regions where maybe planets are forming or maybe life could form someday. And we can also use it to monitor dust. And so dust sounds kind of boring, but in reality, dust are pre-planets. When individual dust particles collide over time, they get bigger and bigger and they eventually form planets. And so this radio and microwave light allows us to view this dust. And if you saw a while ago in the news, the first ever image of a black hole came up by using radio and microwave light, or by looking at spinning molecules. All right, so I'll real quickly go into infrared light. And remember, we're only going through radio, microwave, and infrared today, and talk about how we use infrared light to look at molecules. So how radio microwave is more spinning, infrared is kind of like jumping. So here we have an athlete doing jumping jacks. And so based on the exact unique way he's doing a jumping jack, he'll emit a light at a very unique way. And so molecules can do the same thing. So again, we're going to show water up on the screen. Water can jump and move and wiggle all sorts of different ways. If you're ever looking for a dance move on the dance floor, just think about water and like, how can it move its arms? But this, again, this unique way that water can move is a fingerprint to only water, and no other molecule will have the set number of movement options. And so this allows us to say, okay, is this movement emitted light associated with this movement in space? Yes, therefore there's water there. So infrared light is super cool as well. So it's probably one that more people are familiar with. We can use infrared light to trace heat. So as just a couple of examples, I have Jupiter here in visible light, which is a really cool image. But when we look at it in infrared, we see a lot more details about the individual bands and their structure. And similar to how Michael was talking earlier today, we have these giant clouds in space that absorb visible light that we just can't see through. But if we look at them with infrared light, we can see through them and actually see the stars beyond that cloud, and to learn more about the universe that the visible light just can't see past. So in summary, I'm just going to kind of put a little overall overview of all the different types of lights, even the ones we didn't talk about. So, and to bring it back to the Crab Nebula, if we remember, we had that one image of the Crab Nebula in the visible light. But astronomers, we're going to use all the different types of light to view the Crab Nebula. So, for example, we can use radial light, which gives us a different picture and tells us about molecules and dust. We can also use infrared light, which gives us another picture and tells us a lot about heat. Next, we can also use ultraviolet, which we didn't talk about with visible light, which tells us a lot about the atoms that are in the nebula. And we can also look at X-rays and gamma rays. That tells us a lot about really high energy processes and like explosions. And so astronomers, we combine all of this light to look at the universe and gain a complete picture that visible light and our eyes are not capable of doing on their own. And so astronomers, you could say that when we're studying how light interacts with matter, we're basically watching molecules dance in space.
Woo! Now I got so many new dance moves that I can do. I appreciate it. That's awesome. That was such a good presentation. So many awesome graphics, Abby.
Thanks.
Also, I think I heard some music in the background. It was a little muddled, but it was very nice.
That was my cat's, it's her collar. She has a bell on it.
Okay, well then it was very good timing with the music that the bell started shaking. We got a couple of questions. One in the chat that, I just put the chat away, so give me 1 second to bring that up. But I think it was, here it is. Have any nucleic or amino acid spectral signatures been detected anywhere, I guess?
Depends on who you ask.
So what if we were asking Astrono Abby?
I would like to say yes, but it also depends on where you're talking. So we have detected glycine, which is the most simple amino acid in comets. And so one of the current ideas is that these amino acids and other biologically relevant big molecules form within ices on comets that were delivered to the Earth, basically. And so we have seen glycine in comets. As far as actually detecting these big molecules in molecular clouds or within planet-forming regions, we've not done so successfully yet. But there's a new telescope launching, hopefully in October. Everyone knock on wood, please. Named the James Webb Space Telescope. And that one,
hard. I hope everyone can hear me. Finally launch.
But yeah, that one will be able to look for these big, we call them complex organic molecules. Although don't tell that to a chemist because they'll laugh.
Okay, cool. I was curious if you could talk a bit about the telescope. So you talked about telescopes and different, or not telescopes, talked about different types of light, right? But what about the telescopes that you use for your research, and what type of light do you study?
Yeah, so I actually do mostly theory. I'm learning how to use actual light to observe molecules now. So this is new to me. But I use radio light. There are a few radio telescopes throughout the world. Perhaps the most famous right now is ALMA, which is the Atacama Large Millimeter Array, but we call her ALMA. And so we're able to, so I forget what exactly the question was. I got distracted trying to remember what ALMA stood for.
So I kind of forgot a bit that you did more theory than observing, but it was what types of telescopes and light do you use for your research?
Oh yeah, so yeah, ALMA is a big one. And I am working on a project using ALMA to where we're actually looking at individual substructure of molecules in disks or planet forming regions. And so this tells us a lot, if there's a big gap of water, we're not using water, that one's hard to observe. HCO plus, let's use that one. If there's a big gap of that maybe tells us that something is taking the HCO plus away in that gap. And so that tells us what else could be happening there. I'm getting a little too detailed, but.
That's fine, that's great. There is another question in the Q&A that I just got from Robert Klein. He's asking, is any of the archived data from Arecibo good for you? Do you use the Arecibo telescope?
I have not personally. I don't know if the objects that I study are bright enough for Arecibo. So I study planet forming regions or protoplanetary disks, and they're a bit more faint than some of these other objects. So outflows or things that are being propelled out in gases and stuff are a lot brighter and easier to see. Whereas telescopes like ALMA or other array telescopes, they're called, are a lot bigger and they can see a lot more dim light or a lot fainter objects because they're able to collect more photons. So.
All right, well, unfortunately, I don't think we have time for one more question, but this is my personal question. I was wondering if you could explain your background to the people.
Oh, yeah.
Awesome. And also I wanted to point out that the class that I'm teaching, the literal next lecture I'm doing is on how we use spectroscopy to observe atoms and things in space. So you basically just did my lecture for me. So
You're welcome. Yeah, so this behind me is the periodic table, and every single one of these boxes is a different element. So we have hydrogen up here at the top. And so I didn't talk about visible light during this talk, but each of these is what these atoms look like in visible light. This is their visible spectrum for each one. So.
awesome. Well, thank you, Abby. That was a really great talk. Abby's going to be hanging around in the chat. If you guys want to ask her any more questions, feel free to type those. And yeah, otherwise say goodbye. We should be dancing and everything for Abby, because that's how we observe molecules. So astronomers should be dancing all the time as well. Okay, so let's move on to the next part of the event, and that is trivia. And so I'm going to take a second to pull up the trivia for the day, and give me a second to share my screen. And hopefully that is working for people. We're gonna do Valentine's Day trivia for everyone today. And so in the chat, you should be able to access this trivia at the following link. And the way that the trivia is going to work is that there are 10 questions. Actually, hold up, is this? Sorry, this is working for everyone, right? Can I get some confirmation that everything's looking okay on my end?
I can see the trivia map.
Okay, yeah, it was just looking very weird on my end, so apologies for that. Okay, yeah, so we're gonna do Valentine's Day trivia. Since it is February, you can access the trivia at the following link. And the way that trivia is gonna work is we're gonna have 10 different questions. You can go ahead and answer those questions. If you get the most right at the end of those 10, you can win a couple of prizes that I'll talk about at the end, or talk about right here. We'll also randomly choose winners for prizes as well. And of course, for in-person events, we would give out coasters and posters and things like that. But we'll be shipping those to people if they win trivia tonight. And then also our final speaker of the night, Jeff Bennett, has offered 2 of his books as prizes. So we're going to be giving away 2 of these books as well. The first one is a global warming primer, which is going to be the focus of Jeff's talk. And then also this children's book, The Wizard Who Saved the World, which has been read on the International Space Station, is also going to be available. And you can access those books here. And hopefully in the chat, Catherine has sent that stuff to everyone. All right, so let's go ahead and get going. So first question of the night.
Matt?
Yeah?
If you're trying to screen share, you're not screen sharing.
Oh no, I'm not.
We have a link in the chat to the trivia, which is great, but we can't actually see your screen.
Okay, give me a second. That's what I was afraid was happening. How's that?
Perfect.
Welcome to the virtual world, everybody. The best thing we've learned is to adapt to all of the technology issues that occur. And so I will be adapting right now. I just wanted to remind everyone again then of the prizes. Those are Jeff's book is making them available, or Jeff's making 2 of his books available, A Global Warming Primer and The Wizard Who Saved the World. So thank you, Jeff. All right. So the questions here then, question number 1, Cupid with his bow and arrow of love is a Valentine's Day classic. The Orion constellation, named after a hunter with a bow, can be thought of as the Cupid of the stars. Which star in Orion is likely to be the next to undergo a supernova? I just want to thank Jacob White, who's an organizer for Astronomy on Tap as well, for creating the trivia questions for today. And you'll have until the end of the night to submit your trivia questions. So question 2, February is the shortest month of the year. Speaking of years, which of the following does not significantly impact how long the Earth's year is? Is it A, the mass of the Earth, B, the mass of the sun, C, the Earth-Sun distance, D, the gravitational constant G, or E, none of the above? All right, question 3. Objects become redshifted when they are moving away from us. Due to the expansion of the universe, after some distance, essentially everything is moving away from us. What is the redshift of the farthest known galaxy? Is it 0, 0.1, 1.0, 10, or blue? Trivia question number 4. The cold, dark days of February may make you want to scream, but in space, no one can hear you scream. This is because sound needs higher density material to propagate. What is the average density of space? Is it 1 atom per millimeter cubed, 1 atom per centimeter cubed, 1 atom per meter cubed, 1 atom per kilometer cubed, or 1 atom per entire universe? Give me a second to think about that. All right, question number 5. In addition to being the red planet, Mars is the only known planet in the universe that may be inhabited entirely by robots. How many landers, satellites, and flybys have we humans sent to Mars, including successful and unsuccessful missions? 1, 5, 15, 45, or none of the above, Mars is a myth? And usually halfway through, I just want to remind everyone, of course, of our donations for tonight. We're raising money for the Charlottesville and Albemarle County NAACP in support of Black History Month. And so please donate at the link here as much as you can. Any bit helps. All right, so question number 3. TRAPPIST-1, the star that has 7 Earth-like planets, is on the small end of the size distribution of stars. The small stars are sometimes referred to as red dwarfs. But what makes them red? Is it A, they are moving away from us very quickly? B, they have a high abundance of iron in their atmosphere? C, they have a lower temperature than our sun? D, they have a higher temperature than our sun? Or E, they're blushing because we keep spying on them? Question number 7. The most common type of chocolate on the International Space Station is M&Ms, or so I'm told by Jacob. How long is a day on the orbital period on the International Space Station? Is it 1.5 hours, 12 hours, 24 hours, 72 hours, or the sun never sets on the International Space Station? Question number 8. The planet Venus is named after the Roman goddess of love and romance. The planet is indeed quite lovely, and they say true love knows no lies. But which of the following facts about Venus is a lie? A, it has the largest moon of the inner planets, the inner planets being Mercury, Venus, Earth, and Mars. B, it has retrograde rotation, which just means that it spins the opposite way that it revolves around the sun. C, it is approximately the same size as Earth. D, it is the hottest planet in the solar system. Or E, it is a planet. Which of those following is a lie? Question number 9. Pluto is the most cold-hearted of the solar system's non-planets. The New Horizons spacecraft studied this heart-shaped region on Pluto during its flyby. What is the region primarily composed of? Is it water ice, carbon dioxide ice, or dry ice as it's called, nitrogen ice, hydrogen ice, or vanilla ice? And finally, question number 10, the Rose Galaxy, which is this pretty picture here, would make a great gift for that special someone in your life that has the ability to hold a giant galaxy. So whoever you know that has that ability to hold a giant galaxy, get them the Rose Galaxy. What gives this galaxy its distinctive rose shape? A, it's being ripped apart by black holes. B, it is 2 galaxies merging. C, dark matter interactions in the outer halo. D, a large arm of star formation along the line of sight. Or E, a Valentine's Day miracle. All right, so those are all the trivia questions for today. Make sure to submit those questions by the Google form by the end of the night. So that you can be considered for prizes, and we'll reach out to the winners and random people as well that fill it out in the next week or so after we've compiled all the answers. All right, and so that brings us to the next segment of the night, another new segment that's going to be done by Levi Schultz. And Levi is an undergraduate student at the University of Virginia. Levi is a fourth-year student in their final semester here. Levi is going to be telling us all about what's up in the night sky tonight. So Levi, you can go ahead and start sharing your screen, show your video to us as well if you want. And I have a question for you, Levi. What's up?
All right, thanks for the introduction, Dr. Pryl. Hello, everyone. My name is Levi, and I'll be giving you a bit of a tour through the February night sky. So, first things first, like Professor Ed Murphy was talking about earlier, we have a bunch of different missions to Mars this month. And what's really cool is you can see Mars for just about the entire month. It will be up just past, it'll be high in the sky just past sunset. If you look kind of in the south and try and find Orion's pretty distinctive belt, you should be able to kind of navigate to the right, and Mars will be a pretty bright star-looking object. One of the ways that I like to determine whether or not what I'm looking at is a star or a planet, because planets are so much closer to the Earth than stars, they don't really twinkle. Their light doesn't really twinkle when it comes through the atmosphere. And this is just because since planets are closer, they have like an actual finite size on the sky, versus stars, which are so far away, even though they're much larger than planets, they're so far away that they're essentially just points of light. And so when the light from a planet comes into the atmosphere, even though the air in our atmosphere is bumping that light around, which makes the stars twinkle, because the planets are closer, doesn't really twinkle as much. So like Professor Murphy was saying, we're going to have the HOPE mission from the United Arab Emirates going into orbit around Mars tomorrow, as well as the Tianwen-1 mission going into orbit the day after that. Now, what's really cool is when Perseverance lands on Mars, hopefully, on February 18th, we're going to have a pretty cool event where we'll actually have the moon, which will be just about in its first quarter. First quarter this month is on the 19th, but the moon will be right next to Mars. So if you want to find Mars on that day, it'll be really, really easy. So the moon will stick with Mars that whole evening. So all of those pictures I just showed you, they were from an app called Stellarium. It's a great free app I would recommend to everyone here. You can download it for Mac, PC, and Linux machines. And if you don't even want to download anything, it's even available on their website, just as a web version. It's a great free planetarium software that lets you, go forwards in times, backward in time. It lets you just search for astronomical objects. Sometimes if I'm looking for something I've never gotten to see before, I'll take it out and I can try and memorize the star positions a little bit, so it can help me find things. Next up is the Orion Nebula. So in the constellation of Orion, we see the very unique 3-star belt, which is pretty recognizable. But we also have this, what seems to be a 3-star sheath for Orion's sword. But what I always think is really cool is the middle star in this sword sheath is actually not a star at all. It's a bunch of different stars in the Orion Nebula, which is a star-forming region, like we heard about in some of the earlier talks tonight. So what you're seeing on the right is a bunch of stars forming in the Orion Nebula. And as these stars form and start to shine super brightly with really high energy beams of light or high energy rays of light, they start to push this gas and dust out from the system, which collapse to create the stars in the first place. So what you're seeing is the stars heating up the gas and dust, making those molecules dance, as Abby was saying, and making it shine really brightly in some really cool colors. It's one of the most photographed astronomical objects, I'm sure, not just by space missions. This picture on the right here is from Hubble, but also by amateur astronomers around the world. I definitely encourage looking up some other really cool photos. Further, we also have the Winter Triangle. This is made up of these 3 stars. It's the top of Orion, Betelgeuse, as well as Sirius, which is the brightest star in the night sky, and then Procyon. Now, this Winter Triangle is kind of the counterpart to the Summer Triangle. These are not constellations per se, but they're asterisms. It's just another word for a shape in the sky that we've constructed out of the stars. But what I've always found really cool about the winter and summer triangles is they're kind of signposts for the seasons. You know, you'll see the winter triangle only in the winter, and as you start seeing it set early and earlier, you'll know that the summer months are coming. So it's a nice way for me to remember, you know, how did we keep track of time? You know, it's sometimes, for me, it feels like winter is never going to end, but I know that, you know, back before we had calendars and everything, we still were able to keep track of time using the night sky. I also wanted to point out the Pleiades. So these are located to the right of Orion. I'm pretty sure in some Greek myths, Orion is chasing the Pleiades. They're also known as the Seven Sisters, or Subaru. That's why Subaru's logo looks like the Pleiades. This is an open star cluster. This is kind of like a future, this is like an older version of the Orion Nebula. All the stars have been formed, and they're already starting to blast. They've already started to blast out all the gas and dust in the star formation region, so that there's not really any star formation occurring anymore. And I've always thought it's super cool because the Pleiades are super young in a space context. They're only 100 million years old-ish. And so that means that the dinosaurs couldn't see them. So I've always thought that's pretty fun. But yeah, I think that's it for me. Just wanted to give a heads up to some of the cool things that are in the night sky for this month. I definitely recommend checking out Mars while you can. It's a really easy thing to spot, and it's a lot of fun to track it and watch it move throughout the sky in relation to other stars. So yeah, thanks.
Awesome. Thanks so much, Levi. That was great. Thanks for telling us what's up. Good to know what's up with you. Hopefully everyone gets a chance to observe the night sky. Some point, if you haven't in the recent past, do it some point very soon, if you can. And I think Levi's also going to be hanging around. If you guys have any questions for him in the chat, make sure to chat those, and they should be able to answer them. All right, so let's turn to the final talk of the night. And so the final talk is by Dr. Jeff Bennett. And so Jeff is he joining us from Big Kid Science. Jeff got his PhD from Colorado Boulder in astrophysics, and now specializes in mathematical and science education. He's been involved with the program, for example, where astronauts aboard the International Space Station read books, and some of his books to children. He developed an app called Totality by Big Kid Science to prepare for the upcoming eclipses in 2023 and 2024. He's also an author for introductory astronomy textbooks that are used in classes by UVA. And so I am teaching one of the introductory astronomy courses, for which I am using one of those textbooks, The Cosmic Perspective, that Jeff is the author of. But so tonight, his talk is going to be based off of his book, A Global Warming Primer. And these are some of the trivia prizes that he's made available for us tonight as well. And so, Jeff, you can go ahead and turn your video on and start sharing your screen. And we're looking forward to your talk. So go ahead, take it away, Jeff.
Thank you very much. I assume you can see that okay and hear me okay?
Yes, everything looking good. You did much better than I did. So
Great. And congratulations, Matt, on your PhD and your teaching and everything. Thank you for using my book. So tonight I'm going to give you a hopefully a 10-minute version of what I normally do in an hour or so to talk about global warming demystified. And you see from the title that I'm going to focus on the cosmic perspective part of it, which is the part that comes from astronomy. And just very briefly, if you don't win my book tonight in the drawing or the trivia contest, you can actually read it for free online here at globalwarmingprimer.com. And you can also see videos of when I've done the full hour-long presentation. And I also want to briefly mention, particularly for the professional astronomers, a fairly new group called Astronomers for Planet Earth. You can Google it, which now has 700 astronomers around the world who've decided they really want to put a big focus on climate change and getting the public to understand this topic. And it was through them that I made the connection to be with you all here tonight. So with that, we will turn, as soon as I get this to work right, there we go. So the cosmic perspective part of global warming is the fact that we actually know much of what we know about this topic because of our study of other planets, and in particular Venus. Some of you may in fact know that one of the leading climate scientists of the past few decades, James Hansen, actually started studying Venus and recognized how important it was to our own situation here on Earth. And the way I like to frame this in an astronomical sense is if you look at these two planets, I put them here on this screen and they're to scale. And what you notice right away is that they are both essentially the same size. And from other data that we have about these planets, we also know that if you kind of cut them open and looked inside them, these two planets are, for most practical purposes, as close to being identical twins as any two planets could be, with one exception. And that one exception is their surface temperatures. The Earth has this nice, pleasant surface temperature. Venus, not so much, so hot that lead would melt on its surface. And so from a scientific standpoint, the question that this should raise immediately would be, why would two planets that are so identical in most respects have this one major difference between them? The answer that most people will at first guess is that it comes from the fact that Venus is closer to the sun, but it turns out that that doesn't actually work. And you can actually tell, you can calculate it out and see it doesn't work, but you can tell qualitatively by going up to visit a scale model of the solar system, like the Voyage scale model here in Washington, D.C., right outside the National Air and Space Museum, where we have the whole solar system built at 1/10 billionth of actual size. So you can see there's the sun, which is about this big on that scale, and the locations of Mercury, Venus, and Earth. And if you imagine a giant bonfire here at the sun, and then walking over to Venus and the Earth, well, sure, it's going to be warmer at Venus because it's closer to the sun, but you can probably tell from this that it's not going to be enough warmer to account for this huge difference. And that then creates a scientific mystery. So if it's not just distance, what is it that's causing Venus to be so hot? And in brief, we know that now that the answer is the greenhouse effect, where these molecules of gases like carbon dioxide, water vapor, and methane, represented here by the blue dots, trap heat effectively near the surface and in the oceans, and make a planet warmer than it would be without those gases. You might wonder, how do we know that this greenhouse effect is real? Very briefly, two ways. Number one, laboratory measurements. And number two, by looking at planets, not just Venus, but we can look at other planets and moons that have atmospheres in our solar system. And in every case, the only way we get the correct answer in a prediction of what the planet's temperature will be is by including that greenhouse effect. And I want to point out one very interesting thing about the greenhouse effect, kind of shown here in this calculation on the board here, which is that if Earth did not have a greenhouse effect, the temperature on this planet would be well below freezing. And so without the naturally occurring greenhouse effect from the carbon dioxide that exists naturally on Earth, our planet would be too cold for life. And that brings us to the quick cosmic summary of the greenhouse effect and our tale of two planets, which is that the reason for this difference in temperature is because we have enough carbon dioxide to make our planet livable instead of frozen below zero. But Venus has about 200,000 times as much carbon dioxide, and that's what gives it its extraordinarily high temperature. And I like to think about it in the sense that since we wouldn't be livable without the greenhouse effect is a very good thing for life on Earth, but Venus is absolute proof that it's possible to have too much of a good thing. And once you know that, and once you know that we have been increasing the carbon dioxide concentration in Earth's atmosphere, and this now shows that in the context of the past 800,000 years, then you realize we have a serious issue on our hands. And I like to summarize this with what I call global warming 1, 2, 3, which is that when you hear people talking about how global warming might be some sort of complex, difficult to understand thing, it's not. The basic science is very, very simple. And you can summarize it like this. Number one, through what I just explained to you with Venus, we know for a fact that carbon dioxide makes Earth warmer than it would be otherwise. Number two, through that graph that I just showed you, we know that our use of fossil fuels is adding more carbon dioxide to the atmosphere. And that leads inevitably to the conclusion number three, which is that global warming is going to occur. And in fact, you can see here on this graph of temperature data going back to 1880, it's quite clear that the Earth is in fact warming just as we expect from that 1, 2, 3 science. I'll just show you this NASA video that shows you the regional changes, if it plays. Here we go. This is back in the 1880s. Blue is colder than the 20th century average for that region. Red is warmer than the 20th century average. Early on, you see kind of random fluctuations. But as you keep watching and we move into the 60s, 70s, and 80s, it stops going back and forth, and the warming trend becomes very, very clear. So global warming is real. We know it's real, and we know it's a serious problem thanks to astronomy and the perspective that we get from astronomy. I just want to point out also that this has been known for a long time, and it's only fairly recently that it became a political issue and a political divide. And as evidence of that, I like to show this quote from Margaret Thatcher back in 1989. You may recall that Margaret Thatcher was one of the founders of modern conservatism along with Ronald Reagan. And here's what she wrote in 1989: "What we are doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways." And incidentally, in that same speech to the United Nations, which I have posted on the Global Warming Primer.com website, she then goes on to advocate for very strong action, which unfortunately, more than 30 years later, we still have not taken. I didn't mean to show you this, but it shows you the context of past climate change with the carbon dioxide concentration and temperatures, and you see how closely they line up. And again, that's simply the 1, 2, 3 science being verified. The carbon dioxide is the driver of the temperature changes. And I want to close by telling you that while this is a very serious problem, it is a very solvable problem. We already have all the technology necessary to solve it between some combination of efficiency, renewables, and nuclear. There are many technologies that are being developed that can do much, much more. And the only thing that's been stopping us is the political will. But one of the really interesting things about this is that when you look at the actual cost of fossil fuels, their health costs, defense costs, subsidies, the fact that a lot of terrorism and totalitarianism has been fueled by oil revenue and so on, the annual subsidies for fossil fuels are estimated by many organizations, including conservative ones, at $1 trillion a year in the US and $4 trillion a year globally. That's not even counting future costs of global warming, which means that if we were to change to non-fossil fuel energy sources, we would actually be saving money rather than spending money. And with that, I'll close with the letter that I hope everyone will write to their grandchildren. So the idea is you will write this letter, put it in a time capsule that they will open 50 years from now. And I've chosen this letter to the grandchildren because in 50 years, on average, everyone's grandchildren will be about the age that you are today, which means if you're a college student today, in 50 years, you'll have, on average, grandchildren in college. And if you're retired today, you'll have, on average, retired grandchildren in 50 years. So dear grandchildren, as I write this in 2021, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you are my age. I have examined the evidence and I have decided to, and you write in what you're gonna do. Hope your world is a good one. Love, you. And I hope that we will all decide we're gonna make some real steps to make sure that 50 years from now, global warming has become a problem of the past and not of the future. And with that, I will close. There's the book for adults, Global Warming Primer. For kids, The Wizard Who Saved the World, being read from the International Space Station. And for middle school, I've created a new free online curriculum that you can check out at grade8science.com. And those are the rest of my books. And now I will stop and take your questions. Thank you.
Awesome. Thank you, Jeff, for a really great and important talk as well. We got a couple of questions from the audience. We got a couple of some time for them as well. And so the first one I want to start with, every time I change views, I lose the question. So the question is, so it's clear that Venus has a lot more CO2 and is therefore hotter. But why is that the case? Where did the CO2 come from in Venus? And why doesn't the Earth have that much CO2?
That's a very interesting question. So it turns out on both planets, our understanding is that the carbon dioxide was originally vented from volcanoes along with other gases, including water vapor. And we believe that the total amount of these gases vented on both planets has been about the same. So in fact, Earth has spewed out of its volcanoes just as much carbon dioxide as Venus has. The difference in this case turns out actually is related to their difference in distance from the sun. Venus was just enough closer to the sun that it was slightly warmer than Earth, and as a result, it either never got oceans, or as the sun brightened over time, those oceans evaporated. And so Venus's water vapor stayed in its atmosphere and then later was lost to space through processes I won't go into right now. But on Earth, our water vapor condensed and formed the oceans. The carbon dioxide dissolves in the oceans, and then once it's in the oceans, it, through chemical reactions, turns into carbonate rocks. And so if you actually inventory Earth's carbon dioxide, we have about 200,000 times as much carbon dioxide locked up in carbonate rocks like limestone as we have in our atmosphere, which means our actual total amount of carbon dioxide is the same as Venus's. It's just that because of our oceans, it's locked away where it doesn't heat us up anymore.
Right. Great. Thanks for that answer, Jeff. We've got a couple more questions actually rolling in. People keep asking questions if you have some. This one's from Robert Klein. The question is, how confident are you that the jump in temperature at 1750 was due to humans? And what was the cause? Agriculture? I'm not necessarily sure what that's referring to, but I'm not the expert here in this case. So.
Well, the jump in temperature has happened much more recently. It was the turning up of the carbon dioxide in the atmosphere. It started around 1750 because that was basically essentially the beginning of the Industrial Revolution, which is when we started burning fossil fuels in substantial quantities. And I didn't go into it, but there's 4 solid lines of evidence that prove that the carbon dioxide that we're adding to the atmosphere is from the burning of fossil fuels, including isotopic evidence. And that's all detailed in my book, A Global Warming Primer, if you want to see that there.
Okay, cool. Another question we have, this is an anonymous one. They were asking, how well do you think an astronomy student could transition into a job in climate or environmental science with the background and perspectives that they have?
That's an excellent question. So there are, in fact, a lot of, I mentioned even from Astronomers for Planet Earth, professional astronomers transitioning into this area, as well as graduate students, people with master's degrees, and undergraduates moving into this area. And it's quite possible, and the reason is partly because of what we talked about today. The astronomy actually did play a big role in our understanding of global warming, but also because the things you learn for astronomy, in particular the mathematics and the physics that underlie astronomy, is the same mathematics and physics that goes into climate science. And so you can relatively easily apply those same skills and learning that you have from astronomy into these other areas.
Great, yeah, for sure. I think we have, let me look just, yeah, one more time for a final question. And this one's from Jason Keller. I'm gonna try to summarize it a bit. But the question is basically asking, there have been many studies that have been proved that a lot of the studies that are done in regards to climate change or global warming are sometimes more political based than science based to begin some of these studies. They were wondering is, in your opinion, what do you think we could do to put this back on track to make the studies more science based than political based? Tough question.
Well, the research studies are science based. The economic studies and things like that, who knows what the basis is behind them. But the interesting thing is virtually all economists across the political spectrum have come to the same conclusions about this topic. In fact, you probably have read about the passing of George Shultz at age 100, who was Ronald Reagan's Secretary of State. And he was actually a leader in the Republican Party on calling for action on climate change, did a lot of amazing things. He's behind a big Republican-led proposal for a carbon tax to help address this problem, and did lots of great stuff. And it only kind of became a partisan divide really fairly recently, the last maybe 15 years or so. In fact, even back in 2008, John McCain was the Republican presidential candidate and was very, very strong on the issue of global warming and had plans to tackle it, as did Obama, of course. Why it became a political issue is a little harder to understand, but so is a lot of our current political divide. And how to solve it is probably similar to solving much of the rest of our political divide, which is let's get back to facts and science. Because we can actually all agree and we can actually all move and make a better world that both conservatives and liberals will prefer to live in than the one where we just let things keep going the way they are.
All right, well, thank you so much, Jeff, for the great talk. We don't have much time left, but I think Jeff will be around in case anyone has some last questions for him in the chat. But for now, I just want to say thanks. Thanks for the book for my class as well, and thanks for the talk as well.
Thank you.
Yeah. And all right, and so we have one last thing to do before we say goodbye to everyone, and that is to reveal the trivia answers, of course. And so I'm going to go ahead and hopefully successfully share my screen this time and reveal the trivia answers for tonight. I think it's working successfully this time. And let me go ahead and just present this now. So I want to remind everyone, so we are accepting donations. We're trying to collect donations today for the Albemarle County and Charlottesville NAACP. This link, it turns out, isn't working properly in the chat, but there should be a separate link that you can click on that brings you to the homepage of the NAACP for Charlottesville. And you just have to separately click on the donate button to then go to the donation page. So please, if you can donate some money, any bit helps for sure. So let's go through the trivia answers. So the first question about Cupid with his bow and arrow of love. The Orion constellation is named after a hunter with a bow, which can be thought of as the Cupid of the stars. Which star in Orion is most likely to undergo a supernova? The answer is Betelgeuse in the shoulder of Orion right here. February is the shortest month of the year, but which of the following doesn't significantly impact how long the Earth's year is? The answer to that is the mass of the Earth. And so our year and the years of all the planets are primarily determined by their distance from the sun and the mass of the sun, which also involves this gravitational constant G as well. So the mass of the Earth doesn't really impact the length of our year much. Objects become redshifted when they're moving away from us. And what is the redshift of the farthest known galaxy? The answer to that is 10. What is the average density of space? The answer to this one is about 1 atom per cubic meter. And so much less than what we experience in our day-to-day lives. In space, the average density of space is about 1 atom per cubic meter. All right, how many landers and satellites and flybys have we humans sent to Mars? The answer to this is 45. There's been quite a bunch that have been sent. Hopefully more as we continue, hopefully more even successful missions as we continue forward. But it turns out Mars is not a myth. Mars is real, and we've sent about 45 successful and unsuccessful missions to Mars. The small stars in the TRAPPIST system are sometimes referred to as red dwarfs. What makes them red? The answer is that they have a lower temperature than our sun. And so the temperature of stars effectively sets what color we see when we observe them with the naked eye. And the hotter stars are bluer and cooler stars are redder. And then average temperature stars are yellow like our sun is. All right, how long is a day or the orbital period on the International Space Station? That's 1.5 hours. Every 90 minutes, the International Space Station completes 1 orbit around the Earth. And so you can effectively get a sunrise and a sunset every 1.5 hours. Question 8, which of the following facts about Venus is a lie? That was, it has the largest moon of the inner planets. In fact, Venus doesn't have any moons, as doesn't Mercury. Both Mercury and Venus have no moons. The Earth has 1 moon, which is the largest moon of the inner planets. And then Mars has 2 moons that are about the size of asteroids. Phobos and Deimos are their names. Question 9, what is this region on Pluto primarily composed of? That is nitrogen ice. There's effectively a bunch of glaciers on the surface of Pluto. This particular one is made primarily of nitrogen ice. And final question, what gives this rose galaxy its distinctive rose shape? It is that it is 2 galaxies merging together, creating this very cool image that you can see with some of those telescopes and with the light, the dancing light that Abby was talking about earlier in the night. All right, and so it's gonna effectively wrap it up for tonight. As usual, we try to collect feedback as much as possible to make Astronomy on Tap as fun as we possibly can. This is one of the reasons why we added some new segments that we have today from that Ed and Levi did for us. And so if you have any feedback you wanna provide, you should find that link in the chat. You can just go to this link, which it should work, and provide us any feedback that you possibly can to make Astronomy on Tap better in the future. We're going to have another event, hopefully at the beginning of April, the 1st or 2nd week of April, since we're trying to do this every 2 months. And finally, I just want to wrap the night, as usual, just to thank everyone, thank the speakers, Michael, Abby, and Jeff. Of course, thank all the volunteers, Ed and Levi for doing the segments tonight, and some people behind the scenes, Molly, Jacob, and Katerina. And then, of course, the organizers. I would like to personally thank myself. Thank Catherine for doing a lot of the stuff behind the scenes, Brett, Marilyn, Whitney, and Scott for helping as much as they could in planning the event. And of course, as usual, a final thank you for the about 80 people that tuned in with us tonight. It was a really fun night. I hope you guys enjoyed it. We are recording this. I'll hopefully post it to YouTube sometime in the not so distant future. But for now, I just want to say thanks to everyone for tuning in. And cheers, and I hope to see you next time. So bye, everyone.